In this lesson, we're going to look at the different ways of simplifying radicals, some with variables and some without variables. So we're going to start without variables. And before we get into the rules, I'd like for you to take a moment and just, with your calculator, type in the expression you see on the left here, and then hit enter and look at whatever decimal you get. Then type in, or number that you get, then type in the expression on the right and see if these two expressions are equivalent to each other. If they are, put a check here. If not, put a little X that they are not. So take a moment and do that for all three of these sets. Click pause, and then when you're ready to check, click play. Okay. So hopefully you went through and typed in the left sides and then all the right sides and found that in this first example, the square root of 9 times the square root of 4 is equal to the square root of 9 times 4. So because this remains true, we're going to be able to use a rule for when we're multiplying radicals together that we'll see in just a moment. Now, when you have something like the square root of 9 plus the square root of 4, and then you just put them both under the radical, hopefully you found that those values were quite different. Over here, this is equivalent to the square root of 13, and so that value is not equal to the square root of 9 plus the square root of 4, which you know the square root of 9 is just 3, and the square root of 4 is just 2. So this is equal to 5. So these two sides are not equal. And lastly, the square root of 2 times the square root of 3 plus 5 times the square root of 3 is equal to 7 times the square root of 3. So hopefully you notice in this one it kind of resembles combining like terms in a sense, where what's under the radicals are the same. They all have a 3 under their radical. So because they all had 3's under the radical, we could combine their coefficients outside. So that brings us to our rules for simplifying radicals. The first rule is the square root of a product. So the square root of a product is when you have something like the square root of x times y, what we're going to be allowed to do is break that apart to the square root of x times the square root of y. If it's multiplication under here, you can break them apart, and you can also go in the other direction. So this goes in both directions here. If they are broken apart and being multiplied, you can combine them together under one radicand symbol. The next rule is the sum of square roots with equal radicands. And like I said just a minute ago, this is similar to, in my mind, combining like terms, where if you notice that these are, in a sense, like terms, meaning that what's in the radicand is exactly the same, then you will be able to combine whatever coefficients those radicands have and add or subtract those together on the outside and just write that common radicand value once. So we'll look at that today. And then the square root of a quotient, which we didn't see on the first trial slide, but this says that if we have the square root of a fraction, then we can break that apart into the square root of the numerator divided by the square root of the denominator. And this is similar to the first square root of a product property, where if it's multiplication, we can break it apart. If it's division, you can break it apart. Notice this did not work for addition or subtraction though. Okay, so keep that in mind. Okay. So before we get into practice problems, we'll talk about one more thing, which is that sometimes we will need to take the square root of numbers that are not perfect squares, such as the square root of 45. Now, up to now, you've probably just typed that in your calculator and given the decimal. You may have gotten good at estimating around what decimal this number would produce. You find the perfect squares closest below and above 45, and then you would estimate, okay, this would be somewhere in between. So today we're going to talk about how to fully simplify a radical expression like this. So you can't take the square root of 45. It would be an irrational decimal. So to simplify irrational decimals, what we're going to do is try to find products on the number where one of them is a perfect square. So while 45 itself is not a perfect square, if I think about factors of 45, I could find a factor of 45 that is. For example, I could break 45 into 9 times 5. 9 I would like to use because 9 is a perfect square that I can take the square root of. Now when you do this, you're going to want to choose the highest square root that's a factor of the number. So in this case it's 9 and there's no other higher square root, and so we'll look at that today. So what you would do in your work is show, okay, I can break 45 into 9 times 5, and this is our square root product rule, where if we have multiplication, we can break it apart. So here, if I can rewrite 45 as 9 times 5, and then because I can take the square root of 9, I could break this apart into the square root of 9 times the square root of 5, continuing to break down, which I have down here. And the square root of 9 is 3. And the square root of 5 is going to be an irrational decimal, so we will just write this now as 3 times the square root of 5. So the square root of 45 can be simplified fully to 3 times the square root of 5. And this will be helpful to us when we're trying to combine radicals together. If we can break them down to common radicands, then we'll be able to combine them. You'll see that later today. Okay, so here we are with our first couple of examples, and this is practice just simplifying radicands. So here we have the square root of 12, and this is not a perfect square. However, there is a factor of 12 that would be a perfect square. So, and I'm going to view these from this view from now on so that can interchange between my arrow and pen. But the square root of 12, we can break apart into two factors. We can break it into the square root of 4 times the square root of 3. And you might see this written as just all under one radical. And so I chose 4 and 3, not 6 and 2, because 4 is a factor that is a perfect square. So we always want one that is a perfect square. What can now happen is, because 4 is a perfect square, that portion of this we can take the square root of. The square root of 4 is 2. So this comes down to simplify to 2 root 3. And so I'll show like an arrow out like this. If I can take the square root of one of the parts, I'll kind of cross it out and arrow out what will come out. And that will be helpful when we get much larger or many more expressions under one radical. So anyways, the 2 comes out when we take the square root of 4 to give it 2 root 3. All right, next we have the square root of 50. So while 50 is not a perfect square, there certainly is a factor of 50 that is. And so the largest factor of 50 that's a perfect square is 25. So we can break the square root of 50 into the square root of 25 times the square root of 2. And the square root of 25 is 5. And then we just bring down the square root of 2. Now remember, it's understood that in between this number and this radical is multiplication. That's why you can drop that multiplication sign. And lastly, we have the square root of 72. 72 can be broken down into a couple different perfect square factors. There is 9 that's a factor of 72, but there's also 36. That's a factor of 32 as perfect squares. You're going to want to look for the highest possible perfect square that's a factor of your number. So we're going to use 36 as the factor there. And when you break that apart into 36 times 2, square root of 36 times square root of 2, you can take the square root of 36 as 6 and then just bring down the square root of 2. Now I do want to show you real quick, let's say you forgot that 36 was a perfect square factor and you only thought about 9 times 8, breaking 72 into 9 times 8. You can still arrive at the correct answer. So the square root of 9 is 3. So that gives us 3 times the square root of 8. If you notice that the number you have left under your radical can still be broken down into a perfect square, factor, then keep going with it. So here we can break 8 into 4 times 2 because 4 is a perfect square. Take out the square root of 4, which is 2. Now, if I'm bringing the 2 out and I already have a 3 out here, remember this is all multiplication, so I would do 3 times 2 to give 6 root 2. So you can still get to that same 6 root 2 even if you don't see the largest perfect square from the beginning. Okay, so here's some more practice problems. We're going to do lots of examples today. Here we have 5 times the square root of 48, and the square root of 48 can break down into having a perfect square. The 5 on the outside we'll just keep there, but 48 can break into 16 times 3. The largest perfect square factor of 48 is 16. So from here, the square root of 16 we can take. And so I often like to show this like I was showing earlier as arrowing out, showing that a 4, the square root of 16 is 4. And that means that on the outside, we're going to end up needing to multiply 5 times 4, giving us 20 and bringing down that square root of 3. Okay, let's get into some subtraction here. So here we are subtracting two radical expressions, 10 root 5 minus 6 root 5. Now, normally we can't just go ahead and combine things like this unless what's under the radicand is exactly the same. And in this case, it is. So when that happens, all you have to do is just combine whatever's out front of those. So this is probably more work than you need to show, but 10 minus 6 is 4, and you keep their common root 5 that they both shared. For the last one, we have multiplication here. Now, we're going to multiply the square root of 15 times the square root of 10. You'll notice that neither of these would really simplify further because neither have perfect square factors of their numbers. So there's not a perfect square factor that goes into 15 or 10. However, we're going to use our product rule here, which says that if this multiplication is broken apart, I can combine them. So I can combine the square root of 15 times the square root of 10 to be the square root of 15 times 10, which is 150. Okay, come on. Here we go. So I can combine those. And now that I've got it as the square root of 150, we can now simplify that radicand. So 150 does have a perfect square factor in it, and it is 25. So I can now break the square root of 150 into the square root of 25 times 6. The square root of 25 will come out as a 5. The square root of 6 cannot be taken any further, so it stays as is. So this simplifies to 5 root 6. All right. For this next one, we've got addition here. Remember, with addition, you cannot just go ahead and throw 12 and 75 under the same radicand together. The only thing, or the only option we have here is to simplify each of these separately. And then if once we simplify, we can combine anything, that's when we will do our combining. But at this point, we cannot do any combining. So the square root of 12 does simplify further to 4 times 3. Remember, perfect square we're looking for factors of. And 75 breaks down to 25 times 3. So what I'm going to do is start by just breaking each of these down. Then from here, we're going to be able to take the square root of 4 as a 2 in the first one, and the square root of 25 as a 5 in the second. The nice thing about this is you'll notice when we do that, what we get left with is the same thing under the radical symbol. So now we do have two like terms, like I like to refer to them as, that can combine, where your 2 and your plus 5 outside can combine to make a 7. Oops. And then you just keep that common root 3 right there. Okay, in this next example, we are now applying some of our monomial, polynomial multiplication processes here. So here we have the square root of 2 multiplied by everything inside this parentheses. So to do that, we're going to do some distribution. So root 2 times root 75 and root 2 times 3 root 20 will help us get rid of those parentheses. So let's look at what that looks like. So 2 times 75 comes under the radical as 150. The 3 stays outside. Do notice that you can only multiply what's under a radical by what's under a radical and things outside by each other, but you can't mix and match. So 2 times 20 gives us 40 under that radical. From here, we'll break down these radicals and see if we can simplify them any further. The square root of 150 we've already seen today, and square root of 40 can break down to 4 times 10. So finding those perfect square factors of our numbers, and this will allow us to, again, pull out the 5 here, and square root of 4 will be 2 here. Now when I bring this 2 out, I'm doing 3 times 2, and that leaves us with 5 root 6 plus 6 root 10. At this point, we cannot go any further because what's under the radicands are not the same, so we're finished. All right, here's another one practicing multiplying 2 binomials, but now we have some radicals. So remember, each part gets multiplied by each part. So 3 times 2 is 6. 3 times root 6, it's positive, so we'll write plus 3 root 6. Remember, 3 is outside a radical, 6 is under, so I've got to keep them in their same places. A negative 5 root 2 times 2, well, the negative 5 and the 2 are both not under radicals, so they'll come outside and just bring the root 2 with it. And a negative 5 root 2 times positive root 6 will be a negative 5, and now the things under the radical will multiply to be root 12. So we see that here written more or typed more neatly. From here, we would look to see, can anything combine? And right away, you're saying, okay, none of our radicands are the same. However, we do notice, hopefully, that one of the radicands can further simplify. So we're not completely finished yet. We need to break down that 12 into 3 times 4. 4 is a perfect square, so that we can take the square root of 4, which is 2. So 2 times 5 here gives us a 10 root 3. None of the others simplify, so we just continue to bring them down, and that's as far as we can go. If any of these had the same radicand, then we would combine, but in this case they don't, so we're finished. Okay, I want to use this simplifying radicals to apply the Pythagorean theorem. Remember that the Pythagorean theorem is a squared plus b squared equals c squared, and this helps us find missing side lengths of right triangles. So if I call this side A, this one's B, and this is C, C is our hypotenuse, then we can just fill in those pieces into our formula, where we have A as 6 squared plus B squared plus C 14 squared. So from here, we can simplify to get 6 squared to be 36, bring down your b squared, and 14 squared to be 196. Now to solve for b, we would isolate, so isolate the b squared term, so subtract 36 from both sides, and we're left with b squared equals 160. Now, at this point, hopefully we can, or you would see that to further isolate the b, we'd have to undo the b squared, which means square root both sides. So the square root of b squared simplifies just to a b. And now you have the tools to fully simplify this radical. So the square root of 160, we can break down into 16 times 10. Because 16 is a perfect square, that will come out as a 4. And so we would write the side length of b as 4 root 10. So that's just a way to fully simplify your radicals. All right, let's move on to now look at radicals with variables. We'll be using all the same rules, as we've been using for just radicals with numbers in them. But we'll add or just talk about a couple extra special features about these variable bases under the radicals. So before we take the square root of a variable, let's refresh our memories of the following problem. So let's say we have the square root of 3 squared. Well, under the radical, 3 squared would simplify to 9. And the square root of 9, hopefully you know, is 3. So what I hope you notice is that we end up getting the square root of 3 squared as just the base 3 out of the radical. So with this observation, what would we expect the square root of x squared to be? And we kind of just saw it. But the square root of x squared should just be x, whatever the base was. And I show this often by the radical and exponent of 2 cancel each other out. So using this, we're going to help us simplify variables with exponents under the radicals. Now, really, we could write this as an x to the first. So I want you to think about that. This is really an x to the first. And so what happened to our exponent is we took half of it. So when it was 2, we took the square root of it. To take the square root of an x squared, we actually divide the exponent by 2 is really what's going on there to get the 1. So to simplify radicals with variables, we'll use the same rules as radicals with numbers. What that means is that we're going to see if we can break apart this value of x cubed into a factor of a perfect square and just another factor of x cubed. And what this will look like is, first of all, we cannot take the square root of x to the third because the third, the power of 3 there is an odd exponent. We cannot divide that exponent by 2 cleanly. You can't take half of it cleanly. So what we're going to look to do is break this down to, instead of x cubed, rewriting it as a x squared times x to the first. X squared times x to the first, if you remember your multiplying variable rules, just recombines to be an x cubed. You add the exponents when you're multiplying variable bases. So with that being said, we can break this apart to an x squared times x to the first. Now the x squared piece we can take the square root of. So that will come out of the radical as just an x. On the outside, because the square root of x squared is x, and then there's an x to the first on the inside. So we have x times square root of x as the simplified version here. In this next example, we've got the square root of x to the fourth. Now, when it's an even exponent, you can take the square root of it just by dividing its exponent by 2. So this one's fairly straightforward. All you do is we are able to take the square root of x to the fourth. The whole thing will come out of the radical as an x to the second. Half of 4 is 2 on the exponent, so that simplifies to x squared. For this next one, we've got x to the fifth, and we're going to break that x to the fifth into, because it's an odd exponent, one factor that has an even exponent and one that has an odd. Now, just like with numbers, we always want to break it apart to have the highest perfect square factor that we can. So while you could break this apart into an x squared times x to the third, there is a higher even power exponent that we could use, and that would be x to the fourth. So we'll break it to x to the fourth times x to the first, because x to the fourth we can take the square root of, which comes out as an x squared, half the exponent, giving us x squared times x. And finally, x to the sixth, we've got an even exponent, so just take half of the exponent to be x to the third. What I hope you notice with the ones with odd exponents is we're always breaking them down to, let me erase this so you can see it, an x to the first power times the next highest even exponent. So one step below 5 is 4, so we use x to the fourth times x to the first. Here we did x to the second times x to the first. You're always just using an x to the first times an x to the next lowest even exponent. So that can be a way to think about it. All right, so here's an example that combines numbers and variables. So to simplify something like this, we're going to treat the numbers just like we were doing, and the variables. If you want, you can see this as the square root of 50 times the square root of m cubed times the square root of x to the 6th. But you certainly don't have to break this all apart. That's probably a little more work than you need, but this really is what's going on. So the 50 we'll be able to break apart. The m cubed is an odd exponent, so we'll want to break that one down to an even and an x to the 1st, and x to the 6th is even, so that we'll be able to take the square root of. So that should look like the square root of 25 times 2, which is 50. Then the m cubed breaks to m squared times m to the 1st, and the x to the 6th we keep because it already has an even exponent. At this point, I'm going to show that the 25 will come out. Square root of 25 is 5. Square root of 2 does not go anywhere. We can't simplify that further. But the square root of m squared will come out as an m, and the square root of x to the 6th will come out as an x to the 3rd. So you're left with an m and a 2 under the radical, and outside you have the 5mx cubed. And you're done. All right, so let's try that with this one. How about you try it on your own when you're ready to check it? Pause the video, then click play to check. Okay, so with this one, hopefully you broke your 32 down into 16 times 2. 16 was the largest perfect square factor of 32. Then from there, your p to the 1st, you can't really break down. R can break to r to the 4th times r to the 1st, and t to the 6th is already even. So from here, we will be able to take the square root of 16 as 4. The square root of r to the 4th, that's even, so we can take that as r squared, and the square root of t to the 6th will come out as t to the 3rd. What's left is an r, a p, and a 2 under your radical. And outside, the 4 and the 3 will multiply to give 12, and then the variables you just write next to each other. It's all multiplication. All right, we've got a couple more for you to practice on your own, so why don't you do both of these. When you're ready to check them both, click play after pausing the video. All right, so from here, we can break 12 and x cubed down. And let me just reveal all of it. And then, so 12 into 4 times 3, that 4 comes out as a 2. The x squared comes out as an x, and the y to the 8th comes out as y to the 4th. Take half the exponent. The 3 and x are left under. And for this one, we should combine first to simplify 5 times 3 to 15. 2 times 10 under is 20. X to the 2nd times x to the 4th is x to the 6th. And the y to the 2nd just comes down with everything. Then 20 breaks to 4 times 5. That comes out. This comes out. And this comes out. So the only thing you're left with under the radical will be the 5. And 15 times 2 is 30. All right, two last ones. We can go through these two together real quickly. So the 20 will break down to a 2 times, not 2 times 10. That's not a perfect square. To a 4 times 5. So the square root of 20 will break into 4 and 5 because 4 is a perfect square. A cubed will break to a squared times a to the 1st. X to the 12th has an even exponent and y squared has an even, so we'll leave them how they are. Now we will pull out the square root of 4 is 2, the square root of a squared is a, square root of x to the 12th as x to the 6th, and the square root of y squared as y, leaving us with just the 5, and the a inside. Okay, outside we combine whatever's already there. So if I'm pulling an x to the 6th out times the x to the 1st, x to the 1st times x to the 6th, we use our multiplying variables rules and add the exponents to get an x to the 7th. The -3 and 2 are how we get that -6. Here, this last one's a little bit different. I hope you notice that under this radical, we've got the square root of -40. Because the square root of the number is negative and we don't know what the value of this x is, we cannot take this square root because we don't have enough information to know if this would be a positive or a negative value underneath. So because of this negative sign under, so the opposite of 40x, whatever that may be, we would have no solution here because you cannot take the square root of a negative. That's an imaginary number, and for us, that's as far as we're going to go with that this year. And that brings us to the end of our lesson on simplifying radicals.